Okay, let us start. So this is the fifth and last lecture in my series on computational geometry with bounded workspace. And so today I wanted to talk about more time-space trade-offs. So last time I showed you a time-space trade-off for sorting and for computing the convex hull. And today it will be a time-space trade-off for triangulating monotone polygons, or a time-space trade-off for a problem which allows us to triangulate monotone polygons. And when I'm done with this, I also want to say a few words about lower bounds. So how do you prove lower bounds in this model? What models are there? What assumptions do you need to make for making lower bounds work? Okay, but let's first look at another time-space trade-off. And this was for the following problem. So this I already mentioned last time briefly at the end of the lecture, the so-called ALRSN problem. And the ALRSN problem is all larger, N. ANRSN problem, all nearest right smaller neighbors. That's the name of the problem, and so let me repeat what it is. So the input, it's a set, or it's a sequence x1, x2 up to xn of numbers, and the output is we want all nearest right smaller neighbor pairs. So these are NRSN pairs. And an NRSN pair is a pair of the following form. So it's xi, xj. So it's pairs of numbers in the sequence such that the following holds. So all of these things need to be there, so it needs to be right. So this means xj needs to be to the right of I. So this means the first property is we have j is larger than I. This is the right. Then we need smaller. So xj needs to be smaller than xi, so this is the second condition. And the third condition, nearest, means that all the elements that come between xi and xj have to be at least as large as xi. So we want to have xk is at least xi for k from I to j minus 1. And so a pair of this form is called a nearest right smaller neighbor pair. And what we want is we want to have all the pairs, all the possible nearest right smaller neighbor pairs for this sequence. And so it's we are happy with arbitrary order, in arbitrary order. And so let me visualize this. So it's very easy to visualize this. So here, so you can draw the sequence as a two-dimensional collection of points, right? So this is 1, 2, 3, and so on. And so this is the first number, x1, x2, x3, x4, according to the x-coordinate. And the nearest right smaller neighbor pairs, they look as follows. So the nearest right smaller neighbor for this point would be this one. For this point, it would be like this. For this point, maybe that one, right? For this point, this one. For this point, this doesn't have one. This point has this nearest right smaller neighbor, this one has that, this one doesn't have one, this one doesn't have one. Yes, and so this is what we want to find. And last time I motivated this problem, so why do we want to compute these things? So the application for this is we can use it to, when we can solve this problem, we can triangulate mountains. And a mountain is a polygon which looks like this, right? It's a monotone polygon which has one line at the bottom and a sorted sequence of vertices on the top. Yes, and okay. So now the problem is we want to solve this, and again we have S words of, or S cells. I used to call it as cells of workspace, as before. So we want to have some time-space trade-off. So we want to have some algorithm which gets better as S gets larger, but we will see that here the time-space trade-off, it behaves differently as in the case of sorting and convex size. And so now let's see how to do it. So let's start with describing the algorithm. So how do we do this? So first of all, I define some number h. And h is defined as logarithm to the base of s of n, right? So n is the input size, the number of numbers in the input, and s is the available workspace. And now I do the following. I subdivide x into blocks. So for L from 0 to h, we subdivide x into blocks of size s to the L. And so, and the block of s to the L, and so for a block of size s to the L, we call L the level of the block. Okay, so let me draw a picture. Here. Oh, and so this algorithm and this approach for solving this problem is due to Asano and Kirkpatrick. So this is an algorithm. It's a recent paper by Tetsuo Asano and David Kirkpatrick. Okay, so now let me draw a picture. So how does it look like? So here we have the input x. So this is x, and so this is some array with a certain number n of elements. And so at level equals 0, we have, so at the 0th level, every element of the input is a block, right? At the level 0, every block has size s to the 0, so we have these blocks. Then at level 1, we subdivide the input into blocks of length s, right? So s, 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 like this, right? And then at level 2, we subdivide the input into blocks of size s squared, right? And so on. And then at level 3, we have blocks of size s cubed. And then at level h, we have just one block, right, of size n. Yes, I mean, it's always the same input, but at different levels, we subdivide it into blocks of different sizes. Yes? Clear? And then, so one more piece of vocabulary that we need is, so a block, wrong color. So a block at level L, for L at least 1, consists of S subblocks at level L minus 1. Yes, so I will think of every block which is at a certain level, like this block. It consists of S. So this block here at level 2, for example, has size s squared, and so it consists of s subblocks of level 1 of size s, right? And so we have some hierarchy of blocks on our input. And now I will use these blocks to get some time-space trade-off for finding the nearest right smaller neighbors. And so let me, okay, so everybody understands this block, hierarchical block structure. It's, yeah. So now, what is the main step of an, so what does the algorithm do? So the algorithm has a main step, and the main step is this. So the main step or the main problem that we need to solve in the algorithm. So we want to do the following for a block of level L. Find all NRSN pairs between its subblocks. Okay, so the main step is like this. So here we have a block, it's at level L, so it consists of S to the L elements, and we know that this block it contains of, so this is S subblocks, and so in these subblocks they are at level L minus 1, and so now we want to find all the pairs which go between the blocks, right? So something like this. So a pair which goes from this block to this block, or from this block to this block, or from this block to this block. So all the pairs that cross one of those block boundaries, right? So we want to find all of these. And if we have some procedure for this efficiently, then we can just go, because every pair will have to cross one block boundary, and exactly one, so we just go through the blocks layer by layer, and we apply this procedure to every block that we have, and then we will find all the pairs, right? So this is the problem we need to solve, and when we solve this problem, we have the whole problem solved. Yes? So now we need to solve this problem. Yes? And yes, everybody happy? And so okay, now we want to solve this. And so how do we do this? And so this is essentially just a scan. So to solve this, so we go through the subblocks from left to right. So like this. So let me draw it here. So here we have the subblocks. And now the algorithm does the following. It goes through all the subblocks from left to right, and in each step I have a current subblock which I'm working with. So for example, say in the beginning, let's say I start in this one. So this is my current subblock, and now I want to find all the pairs which end in this subblock, whose right element is in this subblock. So find for each subblock, find all NRSN pairs that end in this subblock. So how does it work? So let's see. Okay. So here we have these two subblocks, and so I start here at the beginning of the subblock, and I want to find all the NRSN pairs which end in this block here. So this is my current block, and this is, say, the block to the left. So I start here because I know that nobody will end here in this block. Okay, so I start here. And now what do I need to do? So I start with the first element. So I want to scan this block from left to right. I start with the first element. And so I compare this element with the element here. And so first of all, I remember does this element here go? So in this case, so I compare the first element of this block with the last element of that block. in this case, if it goes down, then it's fine. So I know this is a pair, and I can report this pair, right? And then if I have found this pair, what do? Then I know I can proceed with my scan. And the question is, where do I proceed with my scan? If I'm in this situation, I can proceed with my scan here to the left, right? Because I know this guy here, this point here is a valid pair, right? And so now if here again I look what the next point is, and now there's different cases, but depending on what happens here, I can find more the nearest right smaller neighbor pairs which end in this guy, right? So potentially there are more people who end here, more pairs. And so in this case, I go to the left, and now what can happen? So there can be somebody which is higher. In this case, I ignore this guy and go and continue. Or there's somebody who is lower, and then there are again two cases. This guy could be in between. Then this means I have found a new pair. Or this guy could be below. This means this guy is not eligible anymore for being a nearest right smaller neighbor. Right? Yes? Do you understand? So, and so what I do is, so in this situation, so I'm here, and let's say the first pair is somebody is down here and somebody is up there. Then I can basically scan until I hit a situation, until either this block is finished, or I hit a situation where some point is below this point, right? And in that case, if that happens, then I need to move this point to the right until I find somebody who is lower than this point. And then I can output that as the nearest right smaller neighbor pair, right? And I can basically, the main strategy is, so at least in the beginning, so I move through this block from from left to right, and through this block from right to left, and I can simultaneously, so I can alternate the moves and until one of these two blocks is finished, right, and output the nearest right smaller neighbor pairs. Yes? Throughout this move. For the first two blocks. Right? Do you believe this? Yes? So this is, I mean, it's easy. So you're here and here. You start with this. So I want to find everybody who ends in this block. I move to this block. I move to that block. Right? And in general, then what happens is, I will, there can be, and I move until one of these blocks, so in each step I advance in one step in one of the two blocks, and either I hit here or I hit there first, right? So one of the two blocks are finished scanning, right? And so let's say the following thing happens, so I finish this block, but in that block there's still some stuff left, which I haven't scanned yet, right? And then the next thing will be, and then I store this position in my workspace. So I remember this pointer here. Okay. Then I go to this block. So this was my first current block. This was the next current block. I'm done with finding everybody, all the pairs which end in this block. Then I go to that block here. Right? So this will be my current block. And again, I do the same thing with these two blocks. I start moving here towards the right and start moving here towards the left. And again, it may be that, again, I do the simultaneous move, and I may hit the boundary here, or I may hit the boundary there first. So let's assume again that I hit the right boundary first here before I hit the right boundary there. So like that, maybe, like this. And then again, for this block, I remember where I stopped. So this is another pointer I can store. And so I can store these pointers because I have O of S. So there are S blocks, and I have S words of S cells of workspace, O of S, so I can store these pointers. Right? And so now let's see. And so now we're done with this block. We move to the next block. So this will be our current block. And then I move again to the right in this block and simultaneously to the left in this block. And now let's assume something different happens. So let's assume that somewhere in this block, so that we hit the left boundary of this block before hitting the right boundary of this block. So we are somewhere, so while scanning, we're somewhere in this block here in the middle, and we hit the left boundary of that block. And so in this case, I continue here to this pointer. So in this block, I'm done. So there are no more nearest right smaller neighbor pairs which go from this block to this block. But there may still be nearest right smaller neighbor pairs which go from this block to this block, right? So it may happen that that everybody in here in between is larger, but here in this block there's somebody who is smaller than this one and everybody in between. So if this block finishes before this block, I just jump to this block and I continue the scan from where I stopped last time. And then I move a little bit further and maybe it stops again at some point so that this one hits first there. That means I update the pointer here for this block, right? And then I'm done with this block and this continues, right? And so I do this until all the subblocks are finished, right? And so this is one scan, yes? And so this takes, how long does this take? This takes time which is linear in the size of the block, right? Because you scan, so each of these subblocks you scan once from left to right and once from right to left, right? So but these scans, they are not continuous, so it's not really a multipass algorithm, but these scans, they may be interrupted and then you resume the scan, but in total, so you only have S blocks here, S subblocks. That means that you can store all these pointers in your workspace, and you have the random access, so you can scan these things in by touching every element once from left to right and once from right to left. Yes? So this takes yeah. Okay, yeah, so I'm not really done. Okay, so we do this, and so this is done through simultaneous left, right, and right, left scans. And the right-left scans of the subblocks, they may be interrupted, but you can you can use the workspace to store the status of the right-left scan and resume it at a later point. For right-left scan, we store scans may be interrupted. And so store status in workspace and resume as needed. Yes? And so this whole thing, again, because we only scan once from left to right and once from right to left, everybody takes this takes time linear in the size of the block. So there's one left-right scan and one right-left scan. Yes? And so this means at each level we spend linear time, and the number of levels is log n to the base s. So this means that the total running time is O of n times log n to the basis of s. So this is total time O of n per level. So for each block size, each block we scan once, and so the blocks, they partition each level. So the total block size at one level is n, and then the number of levels is log to the base s of n. So the total running time is n log n to the base s, total time. And so this is quite interesting. So here we have some different behaviors. So as you remember, last time we saw for sorting the trade-off was basically n squared divided by s. So for constant workspace we have running time n squared, and for a linear workspace we have running time like n log n. So we interpolate somehow linearly. And so here the trade-off is much slower somehow. Already with constant workspace we have running time n log n, which is quite good. But then with linear workspace we can get linear running time. And I think it's an easy exercise to see how you get. I think everybody can come up with a simple algorithm given linear workspace how to find all of these nearest right smaller neighbor pairs in linear time. Yes, so this is somewhat different behavior as before. And so somehow the difference is that here in this case the input is pre-sorted in a certain sense. So the order of the input is already given in the right way, so that we don't have to scan back and forth to find elements of a certain position as we had for sorting. Right? So this makes it faster. And so this means, this in particular implies that we can also triangulate a mountain polygon in the same time. So because as we saw last time, for triangulating a mountain polygon you have to solve this problem twice, once for left nearest smaller neighbors and once for right nearest smaller neighbors. And once you have solved these two things, you just output all the pairs. These will exactly be the diagonals of a triangulation of a monotone polygon, of a mountain polygon. And then you can even extend this algorithm to triangulating monotone polygons, so which is not too difficult, but I'm not going to go into the details of this. So this also means can triangulate monotone polygons in the same time. So by some reduction. Yes? And so this is the second time space trade-off that I wanted to show you. Are there any questions about this? Do you believe it? So maybe one thing which was not so clear is that you need some kind of tie breaking. So you might worry that you output the same nearest right smaller neighbor pairs multiple times. But I think so this you can get rid of by appropriate checking, right? So that you need to make sure that you don't output the same pair too often. So maybe by omitting some blocks. So if there's some block boundary which also appears, so if there's some boundary between two subblocks which also appears at a lower level, then can it happen? Oh, maybe not. Oh no, maybe not. Oh, okay, I think it's fine. No, you don't need to worry about it. There's no worries, the way it works. Yes. Mm-hmm. I think. Good. Yeah. Any more questions about this? Otherwise, I would talk a little bit about complexity theory and lower bound, if everybody's happy. Yes? So, and so here, so this will be more a bit of a survey. So I don't think I will have time to go into too many details, but I will at least give you some idea of how you can prove that things are not possible. So you saw quite a lot of positive results, some of them easy, some of them maybe surprising, and now we will see that there are also some ways of showing that things cannot be done, or at least that it's unlikely that things can be done. So, and there's basically two things I want to talk to you about. So first of all, okay, so lower bounds. Okay, and so the first one is, so we can appeal to complexity theory, computational complexity theory, And computational complexity theory has talked about space-bounded computation for a long time, so since the 70s. And so there are a lot of techniques and insights have been developed, and we can use those in our setting. And so what we can see is, so using complexity theory, one can show there exist problems which are most likely not solvable with O of 1 workspace. So there are some problems for which we can show that they are unlikely to have constant workspace algorithms, and there's also some more difficult problems for which we can show that they will never have a constant workspace algorithm, and also ones which are most likely not to have one, and also ones which definitely do not have any. And so what do we have? So there are the following things. So when we do complexity theory, we have to talk about complexity classes. And complexity classes, they are a set of problems. Formally, it's a set of languages, a set of decision problems. And so the complexity class which is relevant for us, it's called log space. So we have the following class which is relevant. The complexity class which is called log space, which is an abbreviation for logarithmic space. So sometimes you just write L because log space is pretty long. And so log space, in our setting, it would be all. So log space is a set of computational problems, and it's all decision problems solvable with O of 1 cells of memory in the bit model. So right now I'm doing complexity theory, and because we want to prove lower bounds, it becomes much more important to specify what exactly the model is. So in the first lecture I talked about the models and so what exactly your assumptions are, and then in the next 3 lectures that somehow wasn't so important because we talked about upper bounds and algorithms, and there as long as I somehow used some reasonable operations where everybody agreed that this is something that a reasonable computer with a bounded workspace can perform, everything was fine. But now I want to show that something is not possible, and there I need to very much think about what exactly I'm allowed to do. And so here this means that I have to go to the bit model. So the bit model was where we have n elements in our input, and we assume that every cell of the input, it consists of some constant theta log n bits. Yes, so, and then this means if I have constantly many cells with a logarithmic number of bits, then I have a logarithmic space if I count it in bits, and this is why the complexity class is called log space. Yes, and so for example, one of these problems would be one problem which you could solve in log space, as we saw, is given a set of endpoints in the plane, does the convex hull have at least 5 vertices or something like this? This is a problem which we can solve in log space. Or given a tree and 2 vertices in the tree, does the path between these 2 trees have at most 3 length 3, or these kind of problems? So these are problems solvable in log space. And so then the first thing that we know from complexity theory is the so-called space hierarchy theorems. And the space hierarchy theorems tell us that there exist problems which are, so for every resource bound, for every reasonable resource bound which is larger than log n, so maybe like n or log squared n or 2 to the n, there exists problems which are solvable with that amount of space but not less. So this means that definitely by time hierarchy, by space hierarchy theorems, there exist problems which are solvable with more space, but not with constant space. So, for example, so time hierarchy space hierarchy theorems. So I'm not going to prove this, but it is known in complexity theory that, for example, there exist problems solvable with let's say something like O of log n cells, but not O of 1 cells. Yes? So complexity theory already tells us, or even can prove, I mean that's a rare event in complexity theory, we can even prove unconditionally, so this is a theorem that there are, not every problem can be solved with O of 1 workspace. Yes? So not every problem can be solved with O of 1 workspace. This is the first insight. And okay, I mean this is probably not surprising to you, but so we can prove this. And but I won't. And so this is the first thing. But just the fact that there exist problems which cannot be solved with constant workspace does not mean that the problems that we care about are not solvable with constant workspace. And so this is at least some insight, but the insight only takes us so far, because of course in practice as algorithm designers we have a problem which is given to us and we are interested in, can we solve this problem with constant workspace or not? And so now let me show you something else, how you can, for concrete problems, try to find at least some indication that they are not solvable with constant workspace. And for this, let me define another complexity class. So there's another complexity class which is basically the next complexity class after log space. And so complexity class, and this is called non-deterministic log space. And this is abbreviated with NL, non-deterministic log space. And non-deterministic log space is the same as log space, but we add the term, so we add the property that our algorithm can be non-deterministic. And so do you know what it means that an algorithm can be non-deterministic? Is clear, or should I? So it means that the algorithm can make decisions. So at some point the algorithm can branch arbitrarily, and we have to guarantee that that if there exists a way to branch such that the algorithm can say yes, then the algorithm will do it. And we need to design the algorithm in such a way that whenever the answer is yes, that there will be a path which a way of making these decisions such that we get to a positive answer, and if the answer is no, then no matter what decisions we take, we will always get a negative answer. So this is what non-deterministic log space means. But so in PNP, so for polynomial time, you know that this notion of non-determinism is equivalent to saying that there are certificates for the yes instances that can be verified in polynomial time. So here with log space, it's a bit more tricky. I think, I mean, there's also some certificate notion for this case, but you need to be careful what these certificates are and where they are and how big they are and so on, how you can access them. That's why this class is usually defined in terms of non-deterministic Turing machines and not really with certificates, because that's not as easy, or at least more subtle. Okay, and so this is the same thing as log space, same as L, or similar to L. But we allow non-deterministic algorithms. Okay, And now the complexity theoretic assumption is that these two classes are different. So it's not, we don't know how to prove it, but we assume, or it's widely believed, whatever this means, so that this and this is different. So I mean, we know what is clear is that L is a subset of NL, so every problem you can solve with a deterministic log space algorithm. You can also solve it with a non-deterministic log space algorithm naturally, because so here you just add more power to what you're allowed to do. So this is, we know and we believe or assume or find it convenient to believe, so whatever you at least, so we believe is L is not equal to NL, but nobody knows how to prove it. So we believe that this is not equal, so that there are problems which are solvable in non-deterministic log space, which are not solvable in log space itself. And so if you want to show that a problem is unlikely to be solvable with constant workspace, what you can do is you can prove that it is complete for this class. That is one of the most difficult problems in this class. And this you can do through a completeness reduction. So, and for this you need to have an appropriate notion of reduction, which I'm not going to really get into, but I mean, so you need to think of what kind of reductions, so what it means to reduce one problem to another. So you know it probably from NP completeness. And now you need to transfer it to the case of bounded workspace. So you need to have some kind of bounded workspace reduction. So, but you can define a notion of bounded workspace reduction, and with this notion of bounded or say constant workspace reduction, you can define a notion of completeness for this class, and then when you want to show that the problem is unlikely to have a constant workspace algorithm, you just show that it is complete for this class. Or that's one way to show, right? So, so NL has complete problems with respect to some notion of bounded or of constant workspace reduction. So, so I put this into quotes because I'm not really defining what it is. So this is a notion which you need to define what exactly this means. But so if you define it properly, then you can prove that NL has complete problems with respect to this. So this means that there are problems which are in NL, and every other problem which is in NL can be transferred to a complete problem with some constant workspace reduction. And so we believe these problems, so these constant these NL complete problems are unlikely to be in L. Yes? And so let me give you one example. So what's the natural, what is one of those problems for which we believe that they do not have constant workspace algorithms? So here's one example, but there are many more. So one example. So this is so following input G equals VE, and it's a directed graph. And we have two nodes S and T in V, and the output is a path from S to T if it exists. So we don't know if the graph is connected. And so, I'm sorry. I mean, this is it has to be a decision problem, right? So it's not, sorry. So this is not in NL, this problem, because it outputs something which is not 0 or 1. So the output is there a path, directed path from S to T? And so this problem this problem lies in NL, in non-deterministic log space. So if you have a non-deterministic algorithm, then you can very easily solve this problem because you can just guess a path from S to T. So using non-deterministic choices, you can guess the path from S to T, and then you just follow the path through the graph to see whether it's valid, so whether these edges actually exist, of which we guess that they are there. But this problem turns out to be a hardest problem for NL, so if you can solve this problem, you can solve all the problems in NL quickly or easily. Yes, so we believe for this problem, there exists no algorithm which uses constant workspace. Yes, and so this is quite interesting because, why is this interesting? So there are several things. So first of all, you've seen this problem before, or something very similar. And so when you saw this problem before, there was just one difference. I didn't write directed graph. I wrote tree, right? And when I write tree here, well, I mean, then the answer is yes, because it's a tree is connected. But let's not write tree, but let's write forest, right? So if I write forest, then you can solve this problem in linear time. I showed you how to solve this problem in linear time for the case that I don't write directed graph, but forest. Yes. If I remove directed, if I just write graph, then again it's not clear what happens. So and for a long time nobody knew. So when you just write undirected graph instead of directed graph, so the problem it's not clear. So we don't know, or nobody was able to show that it was NL complete, but also nobody was able to show that it was in log space. But this changed 10 years ago, so in 2005, Omer Reingold proved that if you write undirected graph here, then this problem actually has a constant workspace algorithm. So for undirected graphs, you can solve this problem with constant workspace. And this algorithm is quite complicated. I mean, the idea is simple, but it took a long time to find this algorithm, and it needs some quite advanced techniques from complexity theory. So it took like 30 years of building theory and understanding the way what you can do with graphs and how you can manipulate graphs and how graphs behave and how connectivity in graphs behaves, until in 2005 this algorithm could be found. But it is actually true that so this problem can also be solved for undirected graphs in constant workspace. But the running time is not so good. I mean, the running time is polynomial, but the polynomial is pretty big. Yes? And but maybe one more thing to say about this. So, I mean, this is the bad news. So, or at least one way of proving that constant workspace algorithms do not exist. But actually the situation is not so bad. But we know every problem in NL can be solved with O of log n workspace. In this case, the gaps are not so big, so you can also prove that if there's a problem in NL, then you can solve it with a deterministic algorithm with O of log n workspace. So not with O of 1, but with log n. And this is an instance of general theorem by Savage. So it's a simple dynamic programming algorithm, which I also don't have time to explain. But so if you're interested, of course, I can explain it to you afterwards. Which says that if you can solve, I mean, it's an easy, it's not such an easy, I don't know, it's an exercise, medium exercise, or maybe difficult depending on how much you know about dynamic programming. But you can use dynamic programming to solve this problem here with O of log n workspace. And yes, so this is about constant workspace. Showing impossibility results, you can use complexity theory. And then the final thing that I wanted to mention is time-space trade-offs. Can you actually prove something for time-space trade-offs? And or how do people prove lower bounds for time-space trade-offs? So lower bounds for time-space trade-offs. And so how does this work? I mean, actually, so for example, it is known that for sorting, we have the product of time times space. So this is time, and this is space, has to be omega of n squared. So this was shown by, I think, Paul Beam in 91, which is usually cited. So we know, for example, for sorting, one can prove lower bounds for time-space trade-offs, and so here one can show that the product of the running time with the space, it has to be omega of n squared. But so here the space is measured in bits. So the time-space trade-off, which I showed you yesterday, this is not really optimal for sorting because there I measured the space not in bits but in cells, and one cell contains log n bits in the bit model. So this was somewhat suboptimal because here I got a product which was n squared log n, but so the lower bound is n squared, and there are better algorithms than the one which I showed you yesterday, which are more complicated, which achieve also an upper bound of n squared. And so let me at least give you some hints about how this kind of algorithms work. So and so the approach is, so first of all, you need to have some kind of handle onto the problem. So you need to be able to somehow model algorithms which achieve a time-space trade-off in a way that allows us to prove lower bounds about them. So for example, if you remember your first algorithms class, maybe there you proved the lower bound for sorting. And there also it was at first maybe quite mysterious. How would you prove that no algorithm exists which can sort faster than n log n in the comparison-based model? And the approach was that somehow you take some abstract model which models the algorithms that you use, but which is simpler to reason about mathematically, right? So you didn't really look at all the algorithms because there's an infinite number of algorithms, and so you don't really understand what algorithms do. But you found out when you look at the sorting lower bound, or when you want to prove a lower bound for comparison-based sorting, that it doesn't really matter what exactly the algorithm does. So you can model the algorithm by a decision tree, and the decision tree is a very well-structured mathematical object, which it's a tree, so it's easy to understand and easy to prove things about. And as soon as you made the step that you model your algorithm as a decision tree, it's relatively quick to prove this lower bound on sorting. And the situation here is similar. So we need to find some kind of model which models bounded workspace algorithms which achieve time-space trade-offs. And so the model here is, so model the algorithm as a branching program. So not a decision tree, but something which is called a branching program. And so what is a branching program? So a branching program is defined as follows. A branching program is a directed acyclic graph. So it's a DAG. Looks like this. Yes? So it's a directed acyclic graph, and it has one source and several sinks. So one source, several sinks. So here, this is the source. So a source is a node which has no incoming edges, and a sink is a node which has no outgoing edges. And so what else? So this is, and the next thing is, what is the next thing? So each node is labeled. And so it's labeled with two things. It's labeled with a number from 1 to n, or maybe with, and let's say, or with two numbers from 1 to n. Two numbers from 1 to n. And the edges are also labeled. And indeed, it is the case that every node has the same out degree. So every node has same out degree, which is maybe also something like n, or n to the let's say n, and the edges, the outgoing edges, are labeled from 1 to n. Labeled from 1 to n. And so, let's see, so how does it look like? So I didn't draw this too well, but so maybe this might be labeled with 1, 0, 2, 1, 1, 0, 2, 1, and so on. And so what does it mean? So, and here there are also labels like 1, 2, and there may be more edges, 1, 2, 3. But everywhere there should be the same number of edges, so this example is maybe not so good. There should be more edges, but then I would have to draw too much. 1, 2, 3, maybe there may be more edges which go off 1. Okay. And so this is the formal definition of a branching program, but what is the interpretation? So the interpretation is that this branching program is supposed to model the behavior of a constant workspace algorithm. And so we imagine that we have the input x, and for simplicity, we say the input, it has n elements and n cells, and each cell, it has some value from 1 to n. For this model, for proving lower bounds. And now, what we say is the algorithm, so the branching program, it works as follows. So we start at the root, at the node, and there's only one, or at the source, and there's only one source. And then what we do is we read, so we look at the first number. The number here is a 1. And so this is an address. So we read the input at cell 1. And we output the second number. Or maybe we output nothing when we have some special number here. Maybe 0 means we output nothing. But so we read the first number, and we read the first input, and it can be one of n values. And depending on what we read there, we take the corresponding edge, right? So there may be some number here, maybe 3. And then when we read 3, we follow the edge labeled 3. This takes us to another node. Then this other node will again be labeled with some number. So maybe 5, right? And then we read the input at position 5, and then there may also be, there's also the second number, which means that we may output something or not, depending on what exactly the interpretation of the number is. And then we look at the value that's at position 5, and we take the corresponding edge, and we continue until we reach the async, right? So this means every possible input, it defines us a path through this branching program. Right? Yes? And along this path, we output stuff, right? So this means this branching program, it models an algorithm. And the claim is that every constant workspace algorithm, or every bounded workspace algorithm, I can model as such a branching program. Yes? And now we define, but now this is much better, because so this is not like an algorithm which is a piece of code which we don't quite understand, but it's a concrete graph. So it's a directed graph. And so we can now use techniques to understand this directed graph of bounded degree. And then we can define two things. So maybe so I didn't explain all the details of the model very well, but so the point is that we can model every, can model an algorithm as a directed graph. And then we define, so the time, so given the graph, now we can define the time and the space that the algorithm needs. The time is the length of the longest path from a source to a sink, right? So the time is a longest source sink path, right? Because every execution of an algorithm, it corresponds to a path through this graph and a number of steps. So every node here corresponds to a number of corresponds to one step of the algorithm. So it's reasonable to define the time of an execution or the worst case running time of this branching program to be the length of the longest path. And the second thing is the space is defined as the logarithm of the number of nodes in the graph. In the branching program, right? Why is this? Because this node, it's the state, right? So basically the algorithm which is modeled. So if I want to implement this as an algorithm, I need to remember what is my current node, and so each algorithm which implements this needs to store like some label for the current node, and so this means the size can be defined. The number of bits that I need is the number of nodes. Yes? And then the thing is that now you can use graph theoretic techniques. So you assume that there exists. So now you want to prove a time-space trade-off. So you want to say there exists some algorithm which needs time t. And this means that it has to be representable by some directed graph with t layers where the longest path has length t. But then you can show that in order for this to be correct, you need to have many nodes, right? So because if you have too few nodes and the graph is not too, the diameter is not too long, then there may be contradictions, right? And so this is basically how you prove these kind of theorems, right? So then you can, now with these definitions in place, you have some concrete model you can work with, and then you can use graph theoretic techniques to prove lower bounds, to show that certain things cannot exist, right? And that's the approach, but so, yeah, I'm out of time, so I cannot really go into the details. But I mean, at least so this paper by Beam, where he does this for sorting, it's, I mean, it builds on a lot of work before, but at least in this paper, this is very clean and also pretty short and nice to understand. And so this is the main approach. So try to get some concrete model, like branching programs that work in this concrete model to show that certain things are impossible using combinatorial techniques. Yes, and so I think that concludes my series of lectures. But of course, I'm happy to answer questions. As Jason before me, I, of course, would like to thank you all for coming to the talks and for making this winter school an enjoyable and memorable experience. And I hope you learned something. Yes, so thank you. Yes, but so you have a question? Yes? Do you have a question? No? You will just... Yeah, but you have a question. Yes?
What's the model for multipass streaming? This was a randomized.
Yes, so this model is more powerful. So in multipass you're more restricted. And so for streaming, so for multipass streaming you can also use these kind of models. But you can also, so there's like a different set of techniques that I did not talk about, which is called communication complexity, which is another subfield of complexity theory. And so there the idea is that you have to stream, but you always have to go in a certain way. And then, so the workspace that you have is somehow like a way of communicating between the different positions on the tape. And then there are results that you need to communicate a certain amount of bits in order to compute something. And so this is like another set of techniques which are used there, which I did not talk about. I mean, there's more. You can use this, but you can use more. Yes. Any other questions? No? Well, then thank you. Yes.